down. All right, guys. Anyways, for those who joined in late just now, like I mentioned, many weeks for now already, we're actually supposed to have a test next week, guys. I will be testing you on all the thermal physics chapters, mainly being this 2.1, 2.2, 2.3 here, and also 2.4, guys. I highly recommend that each and every one of you guys attempt some of these questions from the exercise booklet, right? Then at least you know how the structure of the question will be, guys. All right. Without wasting any more time, let's go through a quick revision for all of the chapters here, starting from the state of matter here. Guys, like I mentioned, a state of matter, this is quite a simple one, right? There's only solid, liquid, and gas states that we know of, right? Solid going into liquid and liquid going to gas, all these things, I don't think I need mentioning anymore. The only thing worth highlighting right now is sublimation. Sublimation is basically a process where the states skip step, guys. It basically either goes from solid into gas, or it is going to go from gas into solid here. So just remember this word. If not, I think the rest of these words are quite common sense at this point, right? I don't think it needs much highlighting here. All right, then one more thing I would like to highlight is the arrangement of the particles. For solids, usually we say that it's orderly or fixed or lattice arrangement. Either way to say that they are basically very nicely arranged together, right? And then in terms of the movement, in terms of the movement, I mentioned this before, although solid seems like it's not moving, the particles actually vibrating at fixed positions, guys. So you'll see this come out in your IGCSEs quite often as well. So just make sure you know they are not just not moving, they're actually vibrating in fixed spaces. And of course, the gas and liquid particles are free to move about as long as it is within the container or so on, right? Not much to highlight here. Please go read through it yourself. This part is very, very important though, guys. If you refer back to your notes, guys, this part here is basically talking about how the particles actually gain energy and produce pressure here, guys. Now, in your IGCSEs, they love to structure the question and say that, okay, right now there is a container here, and then there is gas particles that are being heated up by a heat source, right? Then they want you to explain in terms of the particles how the pressure inside here increases. Guys, if they ever ask you this, know for a fact that the key word here is the particles colliding against the walls of the container. Why? Because when the particles collide against the walls of the container, this actually produces a force, right? And if you recall back on the pressure formula, guys, pressure is dependent on force per unit area, right? Having said that, it means to say if I have a greater force per unit area of any specific spot, naturally the pressure is going to increase, guys. Very, very important. You must mention that the particles are colliding against the walls of the container, guys. The most important keyword here. So if you refer back to your notes here, guys, it's basically stating that when particles are subjected to heating, it will actually gain energy and move faster. Of course, the opposite will be true as well. When particles are subjected to cooling, right, it's definitely going to lose energy and move slower. If the volume is constant, when an increase in temperature is definitely going to increase the pressure. Why? Because of the increased collision rate of the gas molecules, not just the collision rate, guys, and the collision must be against the walls of the container. The most important keyword here is that it is colliding against the walls of the container, guys. And this, of course, will naturally increase the force per unit area and naturally increase the pressure inside the container as well. I might ask you guys this actually, most likely I'm going to ask you guys something similar to this question next week, guys. Make sure you know how to answer me accordingly, guys, right? Then moving on to this next part here is essentially going to be Brownian movement. Brownian movement is basically stating how the gas particles don't only collide against the walls of the container. Even before they collide against the walls of the container, you will see that they actually move in random zigzag motions already. And the reason why they move in random zigzag motions is because even before it reaches the walls of the container, it will collide with other gas particles, right? And when the gas particles collide against other gas particles here, they will bounce, 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 and so on, right? So in your IGCSEs, if they ever ask about Brownian movement, there are only two specific characteristics. Number one, either they're going to be in a zigzag motion, right? It's going to be in a zigzag motion, or number two, it's going to be random speeds away, guys. Very, very important. If they ever ask you the characteristics here, you have to mention that the particles move in a random zigzag motion and also in random speeds. That is essentially the two key characteristics of Brownian movement, right? Or sometimes known as Brownian motion, guys. Make sure you know this, very important as well, right? Then moving on to this part here is one of the relatively more important part as well. I can see this coming up in your IGCSEs quite often, and you can be sure to expect one or two questions in your test next week as well, in terms of evaporation. Now, in terms of evaporation, you have to be able to explain step by step how evaporation occurs in terms of the molecular structure, guys. And like I mentioned over and over again, in order to explain this, you just need to understand that evaporation will only the quiz will got how many questions are? Probably 4 to 5, or maybe 5 to 6, depending on whether I stumble upon an interesting question or not. Yeah, there's going to be some ABCs, and then there's going to be some paper 4 structured questions. So yeah, I think this will be a good gauge for me to see whether you understand or not. How many MCQ and how many practical? MCQ probably 10, practical probably 4 to 5, depending on whether I want to add more or not. But it's definitely not going to be less than 4 questions. So, and you only have 1 hour, so yeah, just study for it, everybody. Make sure not to fail my paper. Okay, anyways, like I was saying, Hannah, did you just join? Why were you late, Hannah? All right. Anyways, like I was mentioning here, guys, in order to explain how evaporation occurs, you have to be able to understand that evaporation only occurs on the surface of the molecules, right? If you understand that it occurs on the surface of molecule, and you also understand that evaporation is essentially liquid state changing into gas state, right? If you think about it a little bit further, you'll understand that liquid changing into gas state must be when I supply energy to it, right? So from here, if you can remember these basic things, you can more or less bullshit your way through the whole thing, right? So, COVID. Anyways, if they ask you to explain evaporation going on here, you have to mention that, the surface molecules will absorb energy from the molecules below it, right? It must absorb the energy from the molecules below it. Once these particles gain enough energy, they'll break through their forces of attraction and escape to the surrounding as more energetic molecules, right? More energetic gas molecules are. When the energy escapes, what's going to happen is the energy here is obviously going to become less, right? Because it's essentially getting absorbed all its energy already. And when all its energy is being absorbed already, naturally the temperature is going to decrease, guys. So from here, more or less write something down. I think if you take a mental picture of this picture here, right? This very nicely drawn illustration, I think you could more or less at least get 2 out of 3 marks if you know what the keywords are, right? But yet again, it's just understanding that evaporation is liquid changing to gas state and it must have energy. So the question you ask yourself is, where is the energy coming from? The energy is definitely coming from the bottom here, right? If the energy are coming from the bottom, then obviously these guys will be absorbing it. And then if you think about how they change state from liquid to gas, they must break the forces of attraction between each other, right? When they break the forces of attraction between each other, they'll escape to the surrounding as energetic molecules are energetic gas molecules, leaving behind the less energetic one, and thus your temperature is definitely going to decrease, right? So if you look at your notes yet again, this is essentially just a more structured way of what I've mentioned now, right? Evaporation only occurs on the surface. The molecules on the surface will absorb heat energy from the molecules below it. Molecules will escape to the surrounding once enough energy is absorbed to break the weak hydrogen bonds, which is essentially the forces of attraction between each and every one of them. This one here is very important as well, guys. The factors affecting evaporation is definitely a very common question asked in your IGCSEs. You can, when you do the past year papers later on in year 11, you'll definitely see a lot of these things, right? And you all must always remember it's three main factors, guys: surface area, temperature, and also humidity, guys. Humidity is basically how wet the surrounding is, very, very important. Make sure you know these three factors, because more or less they'll structure a question to test your understanding on this. I mean, if you think about it logically, it makes sense, right? So not much explanation needed there. And finally here, this is essentially the pressure changes. Pressure is dependent on two things, right? It's either dependent on the temperature or also the volume here. If you think about pressure and temperature, you can kind of imagine your thermal flask law, right? Every time you open your thermal flask filled with hot water, what's going to happen is there's going to be a pop sound, right? Why is there a pop sound there? It's because your thermal flask, which is housing all the hot water here, all this hot water here, right, is actually heating up the gas particles here. And when they heat up the gas particles, obviously they're going to collide against the walls more frequently, increasing the pressure. That's why as soon as you open the cap, guys, the pressure is actually trying to equalize, guys. It's trying to equalize, and thus it gives off that pop sound, guys. Very important. I think you can relate this to any logical real life experience, but you must understand that pressure and temperature are definitely directly proportional. The greater the temperature, definitely the greater the pressure here, right? Whereas pressure and volume are inversely proportional. You must remember this as well. You can relate this to the compression of a balloon, right? If you ever compressed the balloon before, you'll notice that as you compress it smaller and smaller and smaller, you feel that the balloon is more likely to burst already because the pressure is actually increasing greater and greater and greater, guys. So, just understand that a decrease in pressure is definitely going to increase the volume, and an increase in pressure is going to decrease the volume, guys. They are always the opposite, right? So from here, if you can remember this, then it is essentially the last part here, which is Boyle's law. All right, Boyle's law states that P1V1 must be equal to P2V2, guys. In terms of your calculation, if you ever see like two pressures and one volume parameter, or they give you like two volumes and one pressure parameter here, for sure, without a doubt, it's going to be these kind of Boyle law questions already, guys. Just remember P1V1 equals to P2V2, and then you should be fine. You should be able to do your calculation logically, right? And yeah, in this part here, read it up yourself. It's basically explaining why the smaller volume has a greater pressure. Read it up yourself. I'm not going to dwell too much here because it's quite self-explanatory, right? But it is also important, guys. Make sure you read it yourself. Hey guys, before I move on to the next part, anyone want me to explain further details of anything I've mentioned from this chapter here? This is the best time to ask now, boys and girls, because the exam is next week. Okay, good. 100% absorption rate, just what I like. So moving on to the next part. This chapter is quite an easy chapter. It's basically talking about thermal expansion, right? Thermal expansion basically explains why when something is heated up, the particles or the object is going to increase in terms of volume. In a super simplified short-term explanation, the reason why anything expands is because the molecules vibrate and take up a larger space, right? So, obviously when it vibrates, when they gain energy, the molecules are going to, vibrate in larger space here. Instead of just vibrating in this small space here, it will vibrate in a larger space. But this vibration will not cause the particles to break the bonds, guys. That's why solid particles are always the hardest to expand, simply because the forces of attraction between the molecules are always the strongest, guys. That's why solid particles will expand the least when heated, and gas particles is naturally going to expand the most when heated here, right? So from here, you just need to understand that hot expands and cold contracts. Nothing much to explain here. These are the few examples that we went through during that class, right? We basically talked about why it is important to leave gaps here, and slant it. You can refer to the video if you want a more detailed explanation, but I don't think that's so important. It's just understanding. This part here is important though. This part here, which has came out from your exams a few times before, guys. And in fact, I've made you guys do some of the questions from the past year papers that is related to this part as well, guys. Basically, you know, the structure of the question will be something like, okay, right now, if let's say I have a thermometer here, right? If let's say I have a thermometer here, and then I place it inside hot water, right? If I place it inside hot water, if let's say before I place the hot water, the reading was at this level, as soon as I place it into hot water, the reading level actually drops a little bit, then only it rises to the proper hot water temperature, right? They will usually ask you, why is that initial drop before it rises? Can anyone tell me? The recordings of your topics, yeah, I have it online. I'll send it to you if you decided to join next week as well. But next week is going to be a tennis. So yeah, I'll talk to your mom. Yeah. Anyways, like I was saying here, right? You know, can anyone tell me why it drops again now, guys? What was the reason that caused the liquid levels to drop again? Anyone at all? Okay, then I guess. Oh, yeah. Heat reaches glass first, causing it to expand. Very good, Kunling. You have saved some random person, which was most likely going to be Hannah because she was on the top of the list. But anyways, yeah, the reason why it drops first is because the heat actually reaches the glass bulb first, guys. And when the heat reaches the glass bulb here, what essentially happens is the whole thing is going to expand now, right? And when the whole thing expands, the glass expands first, right, causing the liquid level to drop. The volume here increased, right? But as soon as the heat penetrates through the glass here, right, what's going to happen is it's going to cause the liquids to expand. And we know for a fact that liquid expands more than solid. That's why the rise is always greater than the fall. Very important, guys. This one here, you have to understand this. And from here, they also like to test you on your understanding of responsiveness and also yeah, most likely going to be testing your understanding on responsiveness, guys. The responsiveness of this thermometer is dependent on the thickness of this glass bulb here, guys. Of course, if you have a much thinner glass bulb, the responsiveness is definitely going to be higher. If you have a much thicker glass bulb, guys, if you have a much thicker glass bulb here, obviously the responsiveness is going to be relatively lower because the heat only needs to penetrate through this much to get to the liquid. The heat needs to penetrate through this much of glass before it reaches the liquid, right? Yeah, very important, guys. You must know this. So if you look at the statements here, initially the indicator drops because the round conical flask expands when heated. Later, the heat reaches the red ink and causing it to expand. The indicator continues to rise as the expansion of the liquid is higher than the solid. Please make sure you understand this. It may come out, it may not come out, but it's always good to know, guys. Right. Then moving on to this next part here, we basically talked about how thermometers are always either going to be silver in color or red in color, right? The reason why they are silver in color or red in color is because for all thermometers, all liquid thermometers, we either use alcohol, which is dyed red color, or we use mercury, which is naturally silver in color. Why do we use these two liquids only? What was the reason we use these two liquids? Why can't we use orange juice, apple juice, or saliva or whatever? Can anyone tell me why do we only use mercury and alcohol? Yes, very good, Kunling. It is because mercury and alcohol are the only liquids that expand linearly, guys. Linear expansion means to say the readings are all like equal distance from each other. If let's say you were to place any orange juice, apple juice, or whatever nonsense in here, right, what's going to happen is the readings will not be linear, guys, and thus, it will be like 0, 1, 2, 3, this kind of situation. Very important, you must know this, guys. Whenever they ask about linearity or mercury or alcohol, know for a fact that they are both kind of related. Why do we use alcohol? It's because they are linear. And then why can we assume that the scales here are linear? Is because we're using alcohol or mercury, guys. Very important. You'll always see this in your exam, guys. They love to ask you about linearity in terms of these thermometer experiments. So yeah, make sure you know. And of course, moving on to calibration of the thermometer, usually we must have two fixed points. You see this word a lot in your paper 2 guys. These fixed points, guys, are essentially going to be points where we know certain thing is definitely going to happen. For example, the freezing of pure water and also the boiling of pure water, guys. Regardless of whatever information they give you, if they were to ever ask you two fixed points, know for a fact that it's always going to be 0 and 100 degrees Celsius only, guys. It's not going to be any other temperatures. Fixed points are 0 and 100 degrees Celsius. Very, very important. You must know this, right? Then this page is arguably one of the most important. Yeah, this page is arguably the most important page in this whole chapter here, right? Basically, this here talks about sensitivity, linearity, and responsiveness. Like I mentioned again, guys, I'll mention this. Sensitivity is the ability to measure small changes in temperature, meaning to say, if I have a very sensitive thermometer, it will go like 0, 0 0.1, 0 0.2, 0 0.3, 0 0.4, 0 0.5, blah, 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 all the way until 1, right? Whereas a very non-sensitive thermometer is going to go like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 already, right? That's why this gives the definition of the second statement as well. A small change in temperature leads to a large change in reading. For the super sensitive one, 1 degree Celsius change caused the reading to change this much. For the non-sensitive one, right, the 1 degree Celsius change only led to a change in this much only on the thermometer. Very, very important. You'll see this a lot in your mark scheme, guys. This sentence or this sentence here, right? Make sure you understand what's going on, then it'll be much easier to rewrite it down in your own words. If you just memorize, it's going to be a hard time, guys. Yeah, and then, yeah, these two are very, very important to know, right? Basically, if they were able to test you on your understanding of sensitivity, linearity, and responsiveness, you must know that in order to improve it is to either use a narrower tube or larger glass bulb. Using a narrower tube basically lets the liquid push up more lengths, guys, and using a larger glass bulb essentially has more liquid to push it upwards, guys. So this is what we want, guys. We want it to have large change in reading. That's why we want this here. And I also mentioned that sensitivity is the exact opposite of range, guys. Range is the difference between the maximum and minimum temperature, right? For example, good range will be anywhere from like -10 degrees Celsius, -10 to like maybe 200 degrees Celsius. This is good range. Shit range will be somewhere like 30 to like 100, not even 100, probably like 70 degrees Celsius. Obviously, the distance from the minimum to maximum here is higher and here is lower. That's why this is a better range. This is a not so good range, right? So yeah, very important, guys. The range is basically a difference between the maximum and minimum temperature that the thermometer can read. How do we improve this? Is by increasing the diameter of the capillary tube, which is the exact opposite of this, or decreasing the volume of the bulb, which is yet again the exact opposite of this, guys. Know for a fact that if you increase sensitivity, your range for sure drops. If you increase range, your sensitivity for sure drops, guys. Very important. From here, if you can remember that, then obviously you can remember the ways to improve or to deprove it, if that's such a word, right? And after that, linearity is, like I mentioned just now, to have equal spacing between each readings here. And responsiveness is basically how fast it reacts to temperature change. I'm not going to explain too much here, but this is definitely very, very important, guys. I mean, among all the past year papers that I've seen, I think sensitivity is the fan favorite, or at least the examiner's favorite. That's why every year you can see them testing your understanding on this sensitivity. So yeah, you must know this. Very important. Okay. Yeah, then after that, I've also given you guys a table in your notes. Make sure you know you read through it at least you know what's going on, right? Bloody hell. And finally, this last part here is essentially a thermocouple. Let's be honest here. Who has absolutely no idea how a thermocouple works until this moment? Can anyone tell me? Anyone that don't understand this? Anyone here that don't understand this at all? Maybe you want to raise your hand so that I know if you understand or not. Oh God. And all right, guys. Like I mentioned again, guys, a thermocouple is essentially something that measures temperature difference using metal expansion instead of liquid expansion, right? If you think about how a thermometer works, is basically the expansion of the liquid that gives the reading of the temperature, right? But a thermocouple, instead of using liquid, it will be a metal, guys. It will be a solid. So from here, you know, the thermocouple is essentially made of a galvanometer, a metal X here that is connected to a hot junction and also connected to the cold junction. Then this hot and cold junction is connected with a different metal. So if let's say you say that this is iron, this must be copper. If you say that this is steel, this must be constant, and so on and so on. But the idea is you have to understand that these two are different metals. Oh wait, Hannah, I think you weren't here, right, when I was describing this chapter. Were you here already when I was talking about this chapter? Oh, yeah, I'll send you a video to watch later on. That is going to be like a more detailed explanation. Very important to make sure you watch through it. At least the thermocouple part, right? Then at least you have something to write on tomorrow. I mean next week. Anyways, like I was saying here, this metal and this metal is definitely going to be different. A thermocouple requires calibration as well. So essentially what happens is if I calibrate it, obviously I'm going to use the fixed points as well, which is 0 degrees Celsius and 100 degrees Celsius. Let's just say with these two metals here, right, the reading of 0.0 degrees Celsius and 100 degrees Celsius gives me a galvanometer reading of 0.1 ampere. From here, I basically understand that, you know, hey, the every 0.1 amperes reading from the galvanometer means to say there is 100 degrees Celsius difference between the hot and cold junction. So that's why with this calibration already, right, this baseline here, I can actually use this to measure different temperatures. For example, if today I want to measure something that's super hot, I don't know how hot it is, but obviously I'm going to put the cold junction back into the 0 degrees Celsius. And when I put the two metals into the hot junction, the galvanometer gives me a reading of 0.5 amperes. From here, if 0.1 amperes is a difference of 100 degrees Celsius between the hot and cold junction. Yeah, sure. All right, bye. Yeah. So basically, if I have, where's Charmaine actually? Oh, now I realize she's missing. Anyways, like I was saying here, you know, the difference between 0 and 100, if it's 0.5 amperes, right, 0 degrees Celsius here is essentially going to be 500 degrees Celsius, because I know for a fact that this here is going to be 0.1 amperes for every 100 degrees Celsius mark. So if it's reading 0.5 amperes, it will give me 500 degrees Celsius temperature difference instead, right? So from here, I can also measure something that's very, very cold. Let's say, for example, if I want to measure something that's very cold, I don't know how much it is, but if let's say I put it back into the 100 degrees Celsius mark, right, and the reading here gives me 0.3 amperes, guys. Some students, they'll tell me here is 30 degrees Celsius. Some students, they'll tell me here is 300 degrees Celsius. Some students, they'll tell me some random number. All of it is not going to be true because, yet again, you have to understand this here, it basically tells you the difference in temperature between the hot and cold junction. From here, 0.3 amperes is essentially 300 degrees Celsius difference from the hot and cold junction. So from here, you know, if it's 300 degrees Celsius difference here to here, 300 degrees Celsius difference is negative 200 degrees Celsius, guys. It's supposed to be negative 200 degrees Celsius as your final answer. So yeah, I think a lot of students, you guys always get a bit confused with this. Please watch the video with the full explanation so that you know what's going on. And in the video, I think some of Some of them they even captured the questions from some students as well. So this is definitely going to be helpful, right? Yeah. But this is essentially how a galvanometer, how a thermocouple works out. If they ever ask you a thermocouple in your exam, they'll either, number one, ask you to draw this diagram. Don't write voltmeter, by the way, it's supposed to be a galvanometer. Or they'll ask you about the benefits. Why do we use a thermocouple? It basically looks like a thermometer on steroids, right? So what's the advantage of using a thermocouple? It basically has super rapid response and super large range temperature reading, guys. These two are very, very important. You'll see this a lot in your IGCSEs, guys. So, you must know this, right? Yeah. Yeah. Anyone's got any questions with anything I've mentioned so far before I proceed on to the next part? So, yeah, if there's no questions, then moving on here, this is one of my favorite chapters because it's mostly calculation, right? This second last chapter here is essentially talking about thermal capacity and specific heat capacity, right, guys? I've mentioned this before, guys. I'll mention this again. Most of you guys will probably not remember this because it is very rarely asked in your IGCSEs, right? But let me tell you, most of you guys who can remember this should be able to remember this as well, because the only difference between thermal capacity and specific heat capacity is just the mass component, guys, in the sense that specific heat capacity is Q equals to MC theta, right? Thermal capacity is Q equals to thermal capacity multiplied by theta, guys. MC theta or thermal capacity multiplied by theta. If you can remember this correlation here, right? It's essentially going to, help you answer most of your calculation question, guys. You have to know this because I see this come up like once every 3 years or 4 years for thermal capacity, which all my students for sure they forget. Then I'll tell them, it's because you don't remember what I told you, right? It is very important, guys. You have to remember these two formulas. Q equals MC theta, which is specific capacity, and Q equals to thermal capacity times theta, which is thermal capacity. Okay? Yeah, then, yeah. Oh, and in terms of specific capacity, if they ever ask, right, it's basically going to be this, guys. You have to explain it according to the formula, which is C equals to Q over M theta, right? From here, specific heat capacity is the amount of energy needed to change 1 kg of a substance by 1 degree Celsius. Very, very important, guys. You must know this, right? And then everything else you can read yourself, right? Read yourself. Make sure you understand your calculation here. Then moving on to this next part here is essentially going to be the electrical energy for heat energy, right? Electrical energy to heat energy is essentially just playing around with the normal energy formula, right? Since we know that energy is equals to power times time, in this scenario here, this energy will be heat energy, right? Which is Q equals to power times time. From here, we understand that heat energy is dependent on mass, specific capacity, and theta. Then we understand that, Q equals to MC theta here is equals to the power times time formula. From here, the amount of power that is supplied and how long it's supplied to the heater dictates how much temperature is actually going to increase in specific things, guys. So, just try to recall it according to the general formula, then try to piece everything together, guys. I know some of you guys may be stuck when you're doing the calculation question because you're like, you don't know which formula to use. I would definitely recommend, if you're stuck in this kind of situations here, please write down whatever that comes in your head and try to logic your way according to the parameters given, guys. If you look at the parameters, you should be able to more or less guess what formula they want you to use, right? And then just try it, just plug in everything. The general rule is whatever formula that you use, it can only have one unknown, right? If it has one unknown with one equation, then obviously you're on the right track. If your formula you're using like 2 unknowns in one equation, and then that's just GG, honestly. Okay, then yeah, the final part here is basically talking about latent heat of fusion and also latent heat of vaporization. Latent heat of fusion and latent heat of vaporization is essentially the amount of energy needed to change 1 kg of the substance without any change in temperature from one state to the other, right? That's why latent heat of fusion and vaporization are always flat lines here. The flat lines indicate that no temperatures are changing. It's just that all the energy is absorbed into the bonds, right, to break the forces of attraction. Once they break the forces of attraction, naturally they'll change state from one state to the other, right? There are basically just two formulas here. Q equals to MLF or Q equals to MLV. I think most of you guys still remember this from probably 2 or 3 weeks ago. Q equals to MLF and Q equals to MLV is the amount of energy needed here and here, guys, or either here and here, right? In your exam, if they ever ask you to define latent heat of fusion or latent heat of vaporization, the key, it's always going to be 2 marks, guys. The first mark will be somewhere from here to here, and the second mark will always be without any change in temperature, guys. So if you just write down the formula, all right, Q equals to MLF, so LF will be equals to Q over M, right? From here, you need to understand that number one, it is the amount of energy needed to change 1 kg of a substance from solid to liquid state without any change in temperature. There's no data in this formula here, guys. And if you cannot remember that, then just remember the graph, right? Why is there these flat lines here? Why are there flat lines here? I mean, there's only 2 flat lines, right? But why are there flat lines there is because the energy is absorbed by the bonds. They want to change them from one state to the other. Very important, guys. Okay. Then please read through the definition. Make sure you know how to bullshit your definition across. It's very important. Then check your calculations again here. Make sure you understand all your working, because you never know. Maybe one of these questions will be coming up next week. Yeah, but please read through your stuff, right? Then finally, the last part here is basically the thermal conduction process. Thermal transference process. There's basically 3, right? Conduction, convection, and also radiation. Conduction is usually involving a third-party object. You must heat up the molecules here and then conduct it to here, right? Whereas convection is basically stating that heat will always travel upwards. Heat traveling upwards also gives rise to the convection current, guys, right? And radiation basically states that heat energy will travel in all different directions. Here. Radiation is the only one that can transfer energy through the vacuum of space, guys. Very, very important. That's how the heat energy from the sun is beamed down onto Earth through radiation. Conduction wise, usually they'll ask you, if they ask you about anything about conduction, they'll ask you to explain it in terms of the molecular account. If it's the molecular account, you just have to say, this particle gains energy, vibrate, and pass on energy to adjacent molecule, vibrate, pass energy, vibrate, pass energy, vibrate, pass energy, vibrate, pass energy. This also explains why the particles the heat always travels from hot to cold, right? Because they need to slowly pass on energy from the hotter region to the colder region here. Read this yourself, make sure you understand what's going on, right? Then you can push your way through a little bit. And convection current is basically stating how the density changes, all right? The density changes because the volume, when it is heated, is expanding now, guys. When the volume heated expands, what's going to happen is it's going to become less dense, right? Less dense, then it's going to rise to the surface, displacing the relatively colder molecules, and thus the whole cycle repeats again. So this is how the convection current works. Please read through it yourself. You have to know how it works in terms of the density, because if they were to ask about convection current, most likely they're going to ask about how the density changes and how it goes up and down, right? Anything that flows up is because it's less dense. Anything that sinks down is because it's more denser. Very, very important, right? And then finally, this last part here, radiation, is the only one that can travel through space. You must know this. Radiation is due to infrared. You must know this as well. As soon as you see the word infrared, guys, I want you to straight away think about anything that is hot. Anything that is hot must have infrared radiation. Very, very important. And then, finally, black, white, and silver. You need to know you need to know which one is the better absorber and which one is the better reflector of heat, right? Oh, yeah, sure. Bye. Yeah, but this thing is quite self-explanatory, I think, right? I don't think I need much explanation here. Please read through all the exercises that you have done so far. It's definitely going to help you guys one way or another. Yeah. So, anyone's got any questions with this part? Anyone need to clarify anything that have not understood from this part? Good, excellent. With the remainder 15 minutes that we have left, let me pick some questions for you guys to do. If you look back into your exercise booklet over here, guys, shit, where is it? Oh my god, wait up, let me find my books. Yeah, here. 100 over pages. Let's select some questions to do together, right? Starting from 2.1. Guys, can you bring out your 2.1 exercise booklet and then let me find one question for you guys to do. Yeah, I think we've done this before, right? Have we? Yeah, I think we did. Let me find you guys one question for me to do. For you to do, I mean. Let's do a calculation question today, shall we? Have we done this question before? Can't remember. Hey, everyone, can you guys do this calculation question and let me know the answer here? The energy loss. Is there enough information? Yeah, there is. Hey, can you guys do this real quick? Let's finish this in 5 minutes. Then we'll discuss the answers and we'll move on. It's not going to be correct. Seems a bit small, Kunling. Let me check. Oh, it's okay, man. Hannah, just refer to this. Yeah, just refer to the screen. It's supposed to be an exercise booklet, but yeah, don't bother flipping. Hey, Kunling, I think your answer is wrong, dude. Yeah. Check your units properly and see. That's not wrong. Check your units properly. That's correct, Jerry. Damn. Trust in yourself. Believe in yourself. Hannah, if you still can't find it, just refer to the screen. It's okay. You don't have to do the calculation in your textbook or your book. Oh, nice. Wait, the rest of you guys, where's my answers? $1.75. Nani? Yandim. What formula are you using, by the way? How do you get one? Yeah. Then after that, what do you substitute into your formula? There is no negative energy loss, Hannah, but yeah, those numbers are correct. Okay, yeah, let's go through this real quick. What the hell, Jenny? What? What's going on, bro? How are you getting all these weird numbers? Yo, the formula here is obviously going to be Q equals to MC theta, right? Right. I think everyone should know this lah, right? I think some of you guys may have thought that, oh, usually teachers say that this one should be kg, right? So you go and change it to 0.15. That is absolutely not necessary. Why? Because look at this units here for the C, it is joules per grams degree Celsius, you know. It means to say this 150 grams will multiply by 4.2 joules per grams degree Celsius. And you're supposed to multiply this here. Now, some of you guys actually use negative 24. You don't need to do that because theta is just a change in temperature. It doesn't matter if it changes from 80 to 56 or 56 to 80. The change in temperature should still be 24 degrees Celsius. That's why you cut off the units here, 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 and you end up with 15120 joules, guys. You know, like this is essentially just mathematics at this point here. You need to know that you don't need to change this because this will cut off this. If you change this into kg, you'll get kg per grams, which doesn't work out, right? Yes, Jen Lim. How do you get can I know how do you get like 1386 or 1.75? What went through your mind, Jen Lim? Yeah. Yeah. Yeah, then you try to find one more question. Hey, was this in your okay? Everyone tell me this answer here. I thought 5.51 was the answer because you put it in the chat. Oh, what? No, 5.51 was the timing following, this I just need to follow my timing. Bro. Right. Yeah. Hey, everyone, what should we do? What's the precaution which you do to improve the accuracy of these heat experiments? What can we do again? What did I mention a few weeks ago? Can anyone tell me what do we do if we see these kind of questions in the exam? Anyone? Oh. Yes, very good. Color metal block. No, what the hell? Add insulation, bro. Bro, why do we add insulation? Because we want to prevent the heat loss, right? I think I've spent like a whole 10 minutes explaining about this part here, right? Why do we want to prevent heat loss? Because these calculations here are all assuming that the heater will 100% go the heat here, and then 100% of the heat will be gone to the thermometer reading, which is going to read this. But in reality, we know for a fact that the heat is actually going to be lost, right? Even before it reaches the thermometer, and this heat will be lost here as well, right? Because of that, usually if they ask about precautions in any heat experiments, we always add insulation. Now, very, very important. We add insulation here. And the explanation is to prevent heat loss away, guys. It's always to prevent heat loss to the surrounding. Very, very important. You'll definitely see this in your exam. Oh, maybe not. Yeah, I see all this define specific latent heat fusion, 2 marks here. Don't need to explain this. I think you guys can do it yourself. Let me find one of the realistic questions. Oh, did I make you guys do this question before? Okay, if I ever did, you have to do it again. Hey, explain this to me. Everyone type me your answer before you guys can go today. Type me your answer and then let me have a look. Everyone do this question right now. Evaporation occurs on the surface of molecule of the soil contains the molecule below the molecule Very good answer, Janet. Excellent. That's exactly what I'm looking for. Odds slowly evaporate to the surrounding atmosphere as they possess a higher temperature than those left behind. Those left behind are colder than the temperature. You got the right idea, but not the right wordings, Kun Ling. Yours actually, yeah, let me send you what Jen wrote. Your answer is quite similar to his, just that the wording is a little bit different. Yeah. Can you read through and see what's the difference here? We're talking about the molecular energy. That's the important one, not which one has higher temperature or which one has lower temperature. You get what I mean? Lol. But yeah, you're supposed to talk about in terms of molecules, not just the energy. You got the right idea, just the wrong wording only. Yeah. Jet molecules will skip liquid surface thermometer equipment. Yeah, wait. That's a very short answer, but it's supposed to be something like this. Yeah, guys, always remember the more energetic molecules are actually going to escape to the surrounding, leaving behind only the less energetic molecules. That's why the temperature decreases. That's why it's only 2 marks here, guys. Right? Yeah. Yeah, for those who have not done all my Google Sheet questions, I highly recommend you doing it right before the exam. It will at least give you a basic understanding of at least how the paper 2 questions are going to be like, which is further going to build your foundation now, guys. Please make sure you at least attempt some exercises, because reading can only get you so far. You actually need to do some of the questions, guys. All right, everyone. Yeah, it's going to be an exam next week, basically. All right. Okay, guys, if you have no other questions, that will be it for today. If you have any questions, you're more than welcome to stay back.